Okay, so today we're going to continue with chapter 10. We'll finish it and start the book. So we're going to do chapter 10, the last thing we want to talk about. And I'll also mention the axiom of choice. But we're going to talk about the Schroeder Bernstein Theorem, which I spelled Schroeder wrong the last time. I'll correct the spelling this time around. But there was a question I was asked last class that I sort of want to talk about, just for a little bit. It's not important for us to know, but in terms of, it's some really important ideas of where you can go with all this in chapter 10. It's really a big area in math. Set theory, it's really huge. Huge is actually a good word to represent it. So, I mean, we've been rushing through things pretty quickly, and I just want to make sure that there are some ideas that are not lost on how remarkable all this stuff is. I mean, so to sort of segue into the question and to answer it, I'll probably start here. The smallest infinity we know about, right, is Aleph Null, the count of infinity. It's the smallest one we know about, right? The next biggest one we think is C. We're not sure, but all indications so far seem to say it's C, right? So, but let's look at the smallest one we know about so far, Aleph Null. I'd like you to take a second to appreciate how big that number is, right? It is bigger than anything that we can even conceive actually existing in physical reality. Do you understand this, right? The length of the universe, the volume of the universe, there's a finite natural number that is larger than that number, right? All the particles in the universe, there's a finite natural number that is larger than that number, right? All the subatomic particles in the universe, there's a finite natural number that is larger than the number of particles, right? And any finite number is, of course, less than Aleph Null. I want you to sort of appreciate how big it is. These ideas that I'm writing on the board, and I write this little thing. Oh, we're just going to talk about Aleph Null. Writing that is writing something bigger than the universe, something that you cannot exist in physical reality. It is a huge number, right? Now, when we take a step up to C, and we talk about C, so this guy's already like, we can't imagine how huge this guy is, right? There's nothing in physical reality that we can relate this to, right? Then you jump to C, and what you realize is that C is so huge that this guy is literally nothing. I want you to appreciate that. If you take all the real numbers and you subtract all the natural numbers, you have the same amount of things as you started with, right? Subtracting all these guys, if you take this number and you subtract that number, the result is still this number. This guy is literally nothing compared to that guy. Remember how huge this guy is, right? And then you start to do things like, oh, take the power set of R. This guy is literally nothing compared to that guy. And you can keep going, right? Like, I want you to understand, these are huge numbers that we're dealing with, right? Now, there's something that's going to probably blow your mind here, if this hasn't blown your mind already. I know we've been rushing through it, you haven't really gotten time to stop and think about it. But I just want you to realize what we're dealing with here, right? And you can, of course, take the power set of that and the power set of that, and we can't even imagine what these guys are comparatively. But we can write them down and we can say it makes sense. Beyond that, what you can do is you can think of these guys, these huge cardinalities, as, you know, the size of this guy, right? You can think of 2 to the 2 to the 2 to the r as a set, right? It's a set of functions, right? But the size of the set of functions is just mind-bogglingly huge, right? Now, here's the thing. These are huge numbers. The smallest one we know about is already huger than we can imagine, huger than anything in physical reality. But we can just keep building. We can keep getting larger and larger. And the thing is, we can actually write these guys down, and we can write them down as sets. there are things that are so huge, you actually cannot write them down as a set. They're literally too big for the idea of a set, right? Now imagine how big this guy is. I can write him down and say, that's a set. It's a set of functions. There are things that are so huge, you cannot write down a set to represent the collection of them. They're literally too big for the idea of a set, right? Okay, so remember how huge this guy is. I can write down a set that corresponds to this guy, right? And this is the size of this set, right? I can write down a set that has this number, totally huge, and we can get much huger than that, and these guys, we can all think of them as sets. There are things that are so big, you cannot think of them as sets, right? So we've been basically doing naive set theory where we had this stupid, a set is just a collection of objects. There are collections that are so huge, you can't actually collect them all, right? You can't actually collect everything and put into a set. There are things that are that huge, right? And things that are that huge will consequently not even have cardinalities. They will literally be so huge that they go beyond the concept of infinity. You cannot write down a kind of infinity and say, they are this huge. They are that huge. You can't describe it with infinity. They are something beyond. It's like they're not countable, they're not uncountable, they're beyond the uncountable. They're so huge, we can't even describe them in a set, right? And for example, based on the axioms that we have currently in set theory, the set of all sets is such an idea. You can't possibly collect all sets. It's impossible to collect a set that contains every set, right? It's a collection that is so huge. Right? So consequently, since the set of all sets does not exist, if you ask, what is the number of all possible sets? How huge is that? There is no answer. Like, it's beyond any infinity that I could write down. It's beyond any infinity that can even fit into an idea. Right? It's too huge, right? So cardinalities are really sort of measuring the size of a set. There are some things that are so huge that the very notion of size cannot apply to them, right? Even if you're talking about infinite sizes, it can't, it's too big, right? I can't even go there, right? Imagine like all these numbers. There are things that are too big where, you know what, writing down something to describe the size of this thing is impossible, right? There are things that are that big, right? Some such things, we have to go beyond the idea of a set, and we have to develop what we call classes, right? So all sets form a class. They're not a set, they're a class. They're something even bigger. And not all classes have cardinalities. Some classes are just simply too big. You cannot describe their size. They go beyond the notion of size. They go beyond the notion of uncountable. They go beyond the notion of infinity. Right? And the question I was asked last time was, when I was talking about, we can create all these cardinalities, we can get bigger than C, we were all having fun. And then someone asked the question, I think it was Cody, so what is the size of all cardinalities? Are they a countable number of cardinalities? Are there an uncountable number of cardinalities? Well, that sort of thing you sort of do within a set theory course. I didn't really want to do with it, but I just figured I'd sort of talk about it so you can figure it out. So in case you're interested and you want to go to set theory, this is sort of what you have to look forward to. All cardinalities is a collection that is too big to put into a set. It doesn't have a cardinality, right? The set of all cardinalities, which I'm totally killing the language here because it's not a set, it's a class, right? You can think of the class of cardinalities. It's too big to actually put a number on, right? So you might imagine, you can actually prove this, by the way, but to prove it, you will need the standard proofs use concepts that you'll do in set theory. Like, you have to go beyond cardinal numbers, you have to talk about ordinal numbers and things like that, which I don't really want to get to. But probably an idea of why you can see that that is sort of impossible to measure is cardinality is a property of a set, right? A cardinal number is just a number that represents the size of a set. If you can't possibly collect all sets, how are you going to collect all cardinalities, which are just a description of these sets, right? So that's sort of telling you the difficulties in actually answering that question. So you might say, okay, let's say we assume the axiom of choice and we can sort of make choices, right? Let's say we collect a set, call it A, and this set contains all AI in some index set I, such that the union of the sizes of these guys represent all cardinalities. Might be countable, might be uncountable, we don't know. But let's pretend, let's not get all sets. Let's just get one set of each type of cardinality, right? And we can use the axiom of choice. So I pick one set of size 0, the empty set is going to be in here. One set of size 1, the set containing 1. One set of size 2, the set containing 1 and 2. One set of size 3, right? Throw them into here, pretend we can actually collect these guys. A set of all sets that represent all cardinalities. Not all sets, but you know, enough sets that if I take the size of everyone, I represent all cardinalities, right? So, and if you let B be the set of all AIs, such that AI is an element of A, right? This would be something like set of all cardinalities. Now remember, we're counting these by some index set. I might be countable, might be uncountable. It actually doesn't matter. What you're going to realize is, if you try to collect all cardinalities, you're always going to miss someone. In fact, you're always going to miss an infinite number of people, right? So now if you do something like let C equal the union of all the AIs, right? So I create a collection where the sets represent all possible cardinalities. Now I'm going to make a new set, which is the union of all these sets, right? Now since C equals the union of all these sets, it simply means that each AI is going to be a subset of C, right? Which means, and there's actually a problem where you prove this in the homework, the size of each AI has to be less than or equal to the size of C. Right? I don't know how many AIs there are. There are probably an uncountable amount, but for each of them, this has to be true. But what does that mean? Let's do something like take the power set of the C. Now, what do you realize will happen here? This guy, notice, it cannot be an element of the B that you created, right? Because this guy is the set of all cardinalities of all sets of all possible cardinalities, right? To create this guy, I just showed that all cardinalities will be strictly less than this new set that I just created. And you might say, oh, well, we'll just throw that C in here and then start all over. Well, then I can take the union of that set. And then take a power set again. Right? It would not be possible to collect all cardinalities. This means B cannot exist. You cannot actually collect all cardinalities. Which means this cannot exist. Because B is not a set. It is literally too big to be a set. You try to put them all in a set, and you can't. Someone will always escape from you, and an infinite amount of people will always escape from you, right? So you try to collect all cardinalities, you actually can't do it. You can't collect them all. You can't put them all in a set. There are just too many of them. Every time you think you have everyone, an infinite amount of people will escape you. Even if you started, and it doesn't matter whether I thought they were a countable amount or an uncountable amount, right? Because I'm going by an index set I, which can be uncountable if I wanted to be. But the idea is, there are too many cardinalities. I can't actually capture them all. I cannot put them all in a set, which means I cannot describe how many there are. There are too many to even put a size on them. Right? Remember the size of this guy? Already mind-bogglingly huge. Yeah, the size of this guy
Doesn't exist.
doesn't exist. It is literally too huge to put a size on, right? It is literally too huge to collect them all. It's too big for a set, right? So, at least with our current axioms, the current ZFC axioms which everyone uses for set theory these days, some things are just too big for sets, and therefore some things just have no cardinalities. You cannot describe how big they are. With that, we go into the next theory. Just wanted to take a moment to just talk about the things we're talking about. Yeah, so how many cardinalities are there? An infinite amount. Which infinity? It's beyond infinity. You can't actually describe it. It's a bigger infinity than we can write down, for sure. Schroeder Bernstein Theorem. This is a theorem that's going to help us to actually figure out where two sets have the same size. So this is a German thing. It's pronounced Schroeder, I think. If you're typing it on a keyboard and you don't have that symbol, they'll probably pronounce. They usually replace the O with OE. So you might see that in some text, right? But that's the theorem. It's a very important theorem. We're not going to prove it, but I'm going to mention it for example. It is used to prove. It's the guy that we can prove that the size of the power set of the naturals is actually equal to the reals. This theorem is actually used in that proof. It's a very powerful theorem. To prove it, we need other theorems. One important one. It's important in its own right, which is why I want to mention it. So that A, B are non-empty sets, where B is a subset. If there exists an injective function from A to B, then there exists a bijective function. Meaning, if you can find a one-to-one function from the larger set to the smaller one, then you can find a bijective function from the larger set to the smaller one. It's a very, very important theorem. So, for example, not going to prove it, but I'll use an example. We can show, for example, using this theorem, that the size of the open interval is actually the same as the size of the closed interval. Okay. Which is probably obvious, but even obvious things need to be proven at some point. Right. For example, proof. it is clear that 0, 1 is less than or equal to this guy, right? Because you know that this guy has at least 2 more people. If not, f goes from 1, 1 to 0, 1 by the identity f of x equals x is an injection from 0, 1 to 0, 1, right? So if you're not convinced that's one smaller, I can prove it to you to use that function, right? We know that if there's an injective function from one thing to another, then the size of this thing is greater than or equal to the size of the other. I can create a function, g, let's call it, from 0, 1 to 0, 1 by I think I want this one. No, that actually works. Right? This is a linear function. It's going to be easy to prove it's 1 to 1, right? But notice that you've mapped all of G. You've mapped all of the domain. It literally, the output will be elements between 1/3 and 2/3, right? So you've literally mapped this guy injectively into the other guy, right? This means that the size of this guy must be equal to the size of that guy. Because I can make an injection from the bigger set to the smaller set. So something like that can work. So you might be wondering, well, doesn't this prove that the closed interval is less than or equal to this one? And since you have, this is less than or, the closed interval is greater than or equal to this would prove that it's also less than or equal to that. So can we conclude from that that these are equal? It turns out that's what the Schroeder Bernstein Theorem tells us. Right? It's not a jump that you can actually make, because remember, when your sets get infinite, crazy things can happen. So it is actually something you have to prove. And this theorem is actually used in the proof. So if you look at the SVT, is what I'm going to call this the Schroeder Bernstein Theorem. It's the guy that says for sets A and B such that A is less than or equal to B and B is less than or equal to A. Is that it as an implication? If A is less than or equal to B and B is less than or equal to A, then you can conclude from that that A equals B, right? So we know that this is true with real numbers. In fact, we're going to talk about it, but it actually turns out it is true with infinite numbers as well, right? With cardinalities, this will actually still hold. And the Schroeder Bernstein Theorem is the guy that tells you you can actually assume this is true, right? So it's not only true for finite real numbers, it actually works for cardinalities. So it will work with Aleph null and C and all those guys, it will still work. Once something is small enough to put in a set and we can describe it with a cardinality, then the cardinalities will be anti-symmetric. theorem. Okay, right now I want to talk about some closing remarks. That's basically the only thing we're going to do for chapter 10. Schroeder Bernstein Theorem was the last one. I recommend you read the proof. It's sort of too lengthy for me to go through. I don't really want to do it, but it's a very important theorem. It's the guy that allows us to show, if you can show there's an injection from one set to the other set and an injection from the other set to the first, or somehow prove that one is less than or equal to the other and that relationship is reversed, we can actually assume that they're equal. Again, it seems like an obvious fact, but there are many obvious things that turn out to be wrong, so it's something that has to be proved. There's a theorem. It's called theorem A. For any sets A, B, one of the following are true. One, either the cardinality of A is less than the cardinality of B, or two, cardinality of A is greater than the cardinality of B, or three, the cardinality of A equals the cardinality of B. Again, it seems like a trivial property is based on the real number system, but remember, for cardinalities, where the numbers can get really huge, bad things can happen. So if you wanted, you'd hope that this would be true. It turns out it actually is. And it's not as trivial as you might think. To prove this, you sort of need the axiom of choice. There's another theorem, theorem B. Do I have enough space to write it down? If A and B are sets, this theorem we actually have before. It sort of looks like a Schroeder Bernstein. And G goes from B to A is 1 to 1. Then A equals B. So the closing remarks at the end of your text sort of say, at the end of this chapter sort of say that, theorem A, you can use it to imply theorem B, right? So you can actually use this guy also to prove the Schroeder Bernstein theorem. But theorem A requires the axiom of choice, which you heard me mention a couple of times. But let's actually talk about what this guy is. We're not going to go at length with it. You can actually use the axiom of choice to prove some crazy things. In fact, math turns out to be a lot more interesting if we assume this axiom, but it's sort of controversial. We're going to sort of talk about why that is, and then we basically move on. There are many ways to state it. For every collection pairwise disjoint sets, there exists at least one set that contains exactly one element. is the axiom. Equivalently, what we can say is there exists a choice function for every collection of sets. i.e., a function that chooses exactly one element from each set in the collection. Basically what I'm saying is, if I have a set of AI such that I is an element of some index set, then we can create a new set B such that B is just a set of all xi such that xi is in A. Basically, whenever you want to choose something from sets, you need the axiom of choice. So it's called the axiom of choice. It's talking about choosing. So for example, earlier when I was talking about, suppose you collect all sets that represent all cardinalities, right? Basically what you need is, you'll sort of gather all sets that have cardinality 0. Choose one. Gather all sets that have cardinality 1. Choose one. Gather all sets that have cardinality 2. Choose one. Gather all sets that have cardinality 3. Choose one. Right? So basically, if I collect all these sets, and even if they're disjoint, we're assuming they have no elements in common. Right? We can say AI intersect AJ is empty if I not equal to J. Right? Even if they're uncommon. So I have a collection of sets. I can literally go through and pick one element out of each set, and then make a new set of all those elements that I chose, right? Which is sort of what I use to create the set of all sets that represent certain cardinalities, right? I actually use the axiom of choice to make the choice, right? A couple of reasons why something like this is controversial is it doesn't really tell you how to choose. It doesn't really tell you how to create the function. It's very vague, and it's just not it's not definite enough to actually sort of make sense. Axioms are usually things where, okay, we know we can do this. Like, all logic and reason tells us we can do this, right? But when you say, oh, you can just choose something. What do you mean just choose something? How do I choose it? At random? Like, is there a process to this? Right? You can't just say, oh, this function exists, and you give no reason for believing that such a function would exist, or how it would even work, right? So, you don't always need the axiom of choice. Bertrand Russell, for example, had this analogy where he was like, you know what, suppose you collect a set of all pairs of shoes in the world, right? And you want to choose one shoe from each pair. It's easy to create a function that does that, a specific function that does that. You can just say, let f be the left shoe in the pair, right? So I can tell you exactly how you're going to make the choice. I can say, go through all the pairs, pick the left shoe. That's great. Where you need the axiom of choice is for the socks, right? Because there is no left and right sock. How do you tell me how to choose a sock? Give me a definite rule that I would know, okay, hey, this is the sock I'm supposed to pick, exactly. No, the two socks are sort of identical. How do I know which one to choose, right? It's sort of like you're telling me to do something, but you're not telling me how you're going to do it. I don't even know if it's possible, right? I mean, it's sort of course, you think you choose randomly. But it turns out when you have like an infinite number of things, this choice actually seems pretty daunting. Like, how do you actually make a choice from an infinite number of things? Right? It's sort of weird. Another reason why it's controversial is that you can actually use this axiom to prove all sorts of crazy things that seem to not be true. So, for example, you can use it to prove a general well-ordering principle, right? So remember what we said well-order means. It means that if the set is non-empty, every subset will have a least element, right? You can actually prove with the axiom of choice that every non-empty set is well-ordered, right? So if you assume this, it'll be the same, it's actually equivalent. There's a by-implication with this and the theorem that every non-empty set is well-ordered. And then people are like, look at that set. There's no least element, right? But that thing is, we're thinking of ordering the numbers based on the natural order like this. Basically, the axiom of choice says, there's a rule that you can order these numbers in such a way that any subset will have a small element, a smallest element. I'm not going to tell you how to do this, but it's possible, right? And that sort of thing is kind of why people are like, especially when the axiom of choice was just starting to take ground, people are like, oh, I don't like that, that's sort of weird, right? You not telling me how this is done is sort of weird, right? You can't just tell me, oh yeah, I can arrange these numbers in such a way that there's a least element for every subset. How? Right? Every notion of order that we can figure out for something like ordering a set of real numbers, we can't find a way to get a least element from every subset here.
So do we need to know that?
No, this is beyond this class. Again, this will be something that you'll do in set theory, right? The set theory class will get more into this. I just thought I'd mention it. Your textbook does mention it. And if you hang out with a lot of math people, you'll no doubt hear it mentioned all the time. So it's sort of vague on how you would actually make the choice, and it's sort of equivalent to things that seem to be crazy. So a lot of people don't like it, but the idea is most mathematicians now today accept it. Some still sidestep the issue. They're writing a textbook, they'll like say in like the introduction, we assume the axiom of choice through this textbook. So anywhere you see me making a choice of something, just assume we can do it, right? There are other people that are like, okay, we're not assuming the axiom of choice. It turns out that you have a richer experience by assuming, right? You can prove more things, you can prove a lot more interesting things if you assume you can make the choice, right? If you can't make the choice, it actually restricts you a lot, and then we have a lot more unanswered questions. So to that end, most people these days are sort of, okay, let's just assume we can do this so we can get to some interesting mathematics. So that's sort of where we will end. Did I want to mention anything else about that? Oh, yes. Another question that we had a couple classes ago. This is needed to prove, for example, if B is any uncountable set. Any one. Pick a random uncountable set. I don't care which one you pick. And A is any countable set. choose a countable set, I don't care which one you pick, then the size of B is strictly greater than the size of A. It seems to make sense that if you take an uncountable thing and you throw away all the countable things, it doesn't make a difference. This guy's literally much bigger than that, strictly speaking. Right? You can never have an uncountable set equal to a countable set. We actually prove that. But to prove that one is strictly greater than the other, no matter who you pick to represent you, is sort of something you need the axiom of choice for. Because then you have to worry about, how do I make the choice, right? You have to show that any choice this will work for. The size of R is greater than any countable set that you can possibly pick. And the size of any uncountable set other than R would be greater than any possible countable set that you can actually pick, right? You actually need the axiom of choice to prove something like that, which we want to be able to prove, right? So that's also something that we might be interested in. That sort of ends our discussion of chapter 10. That's where we're going with sets. Between the homework and the review that I gave you guys, which will work for the next test and the final, you'll have plenty of examples to play around with these ideas.
When will you post the answers to the
Wednesday night? Tonight is Wednesday. It'll be posted in time, don't worry. I know we don't really have a lot of time before the final. It'll have to be Monday because we don't have class on Tuesday. So for the final, I'm going to make the problems on the final very, very similar to the problems on the review and on the test. I'll probably even take some of the exact same problems actually, so I don't have to worry about making up new ones. Right, so I'll probably just pick a one. So I'm thinking so the final. So first thing I want to mention that it will only cover topics after the first test. Alright, so I'm not going to ask you to prove something like expert is even if only that is even. Like, no, we're beyond that, right? Stupid stuff. Right? So it'll only focus on the second part of the course. Very similar to the review, which I will give you the solutions for. Probably some repeated questions. It will have somewhere between 5 to 8 problems. It will be given during regular class time. So I'll write a final that you can do in an hour and 40 minutes max.
Isn't the time of final 2 hours 15 minutes?
During the summer, we don't follow that. During the summer, we do it the length of the class. That's the standard procedure. Everyone will write a smaller final than they would in the full semester. So it's going to be during class time. What else can I tell you about the final? I'd really like, well, I'll talk about that in a bit. So, something I haven't really done this semester that I'd like to do on the final at least is have maybe one question that's a bunch of true or false questions. Sort of figure out, are there some nice questions I can ask you that, oh, it's true or false, right? And of course, I try to make them confusing.
Will that be a bonus or
No, it'll be like one of the problems. If I can come up with enough, if I can come up with like 4 or 5 true or false questions that are really nice, I'll just make that one of the problems. So part A, B, C, D, E, and I give you a statement, I say true or false. And you won't have to write a proof for it, but I might ask you to just write some small sentence of justification, some sort of mathematical intuition that you believe. Well, there are actually a lot of problems on the review that can be solved in a short period of time. I'll just say it's similar to the review. Don't worry about it. I'll make sure it's fair. I started, I didn't finish. I'm sort of thinking what questions, other questions I want to throw in.
Should be 8, 9, 10, and then this chapter, and then
It'll cover everything we do up to today. So we definitely won't finish all of chapter 1 in the next book. And the stuff I'll talk about is sort of stuff that wouldn't be hard anyway. It's much easier than set there, that's for sure, what we're going to be covering. Yeah, it's actually okay, now we're moving on to book 2. We're only going to do one chapter in book 2 and not all sections from one chapter. We're sort of going to pick out some highlights. So this is elementary analysis. By Ross. A very good text for advanced calculus. It's a standard text among a lot of schools, so if you know how to deal with this textbook, you'll be in good shape no matter if you're going to transfer to somewhere else, you'll be in good shape no matter where you transfer, pretty much. So we're going to talk about chapter 1. Goal is first 4 sections. Maybe 5 sections if you can fit it. The last section is very short. It's just saying we create an extended real line by considering infinity and minus infinity as numbers, and we can do arithmetic with them. But that's sort of the way you think arithmetic with infinity would work, right? So you consider plus infinity to be that real number that's greater than every other real number, and minus infinity to be that real number that's less than every other real number. And if you take infinity plus any finite real number, it's just infinity. And if you take infinity minus any finite real number, it's just infinity. Right? It's sort of just going through how you think infinity would work. It sort of shows you that we consider that's how it works, and it actually is consistent. So section 1 is talking about the set n, which we've done pretty much everything about the set n that we want to do. The highlights here in this section, I didn't even list this section in the syllabus. That's how, compared to what we've done, that's how trivial it actually is. But I do want to mention something, just for historical reasons, called PML axioms. It's basically the set of axioms that define the properties that the real numbers hold. And pretty much everything we proved about real numbers, we'll be able to trace it back to one of these properties. There are 5 PML axioms. So, N1 is the first axiom, as it's called. It's simply the axiom that says the number 1 belongs to n. N2. If n belongs to n, then its terminology is successor, which is the number n plus 1 belongs to n. N3. 1 is not a successor. Of any n. And 4, if n and n in n have the same successor, then n equals n. And 5 is a subset of n that contains 1, and for every n it contains n plus 1. Such a subset must be equal to n. These are called the P&L axioms. They are very, they're how the natural numbers were defined axiomatically way back when. Basically, every property that we know about the natural numbers can be derived from one of these axioms. It's sort of, you just define a bunch of properties that you want the set n to have, and then pretty much everything else flows from there. And you sort of assume the minimal things that you want to be true. You have to be very minimalistic when setting up a set of axioms. All right, so remember, the natural numbers were created to be counting numbers, right? So you want to count your sheep or your cows or how much money you have. Basically, if you're creating a number system where you want to count things, you'd want that system to have these properties. And someone thought very long about that. Section 2 actually talks about the rationals, I think. We'll spend a little bit of time here because there's a specific theorem that I want to talk about. So let's talk about the highlights here. We're not going to do everything. Algebraic and transcendental numbers, and we're going to talk about the rational groups here. So definition. A number is called algebraic if it is the solution to a polynomial equation where all the Ci are integers. Right, so you can make all your constants be in the rationals, that's fine. All you do is multiply both sides by the LCD and you create integer coefficients, right? So any number that can solve a polynomial with integer coefficients, we call that number algebraic. we're going to mention something crazy in a bit. We assume that, of course, the Cn is not equal to 0. That's the guy that defines the degree of the polynomial, which you know about already, but we'll talk about it. Here's some facts. All elements of Q are algebraic. Right? Every single rational number is the solution to some polynomial. In fact, we know that there is some the solution to a linear polynomial. So, example, say you have P over Q is in Q, then this solves Qx minus P equals 0. So every rational number will solve a linear equation. So every rational number is actually algebraic. Turns out that some irrationals are also algebraic. Example, radical 2 solves the polynomial equation x squared minus 2 equals 0. Right? So radical 2 is an algebraic number. There's a polynomial with integer coefficients that is actually the solution. So radical 2 is an algebraic number. I will write down some almost anything that you can write down as the nth root of an integer are algebraic. Right, so the cube root of 5, all that algebraic. You can have some crazy numbers that are algebraic, crazy looking, although all numbers are beautiful. For example, x equals, what's an example I have here? The cube root of 3 plus the square root of 7 is algebraic. How do you know? Well, this would mean that x cubed is equal to 3 plus radical 7. This would mean x cubed minus 3 equals radical 7. This would mean x cubed minus 3 squared equals 7. This would mean x cubed minus 3 squared minus 7 equals 0. So this number solves the above equation. And it's a polynomial with integer coefficients. Right? So if you look at that number, it's actually hard to tell whether it's rational or irrational, by the way. I'm going to mention an example about that. But it's algebraic. It actually solves a polynomial. And basically what you try to do is you set x equal to that number and try to see if you can get rid of all your radicals and all your weird symbols and construct a polynomial from it. And once you can construct a polynomial from it, it's algebraic. Once you can construct a polynomial with integer coefficients, that is, then it's denoted to be an algebraic number. Time for some mind-boggling. There are a countable number of algebraic numbers. Right? If you look at the solutions to all possible polynomials with integer coefficients, you can only find a countable number of them. So, of course, what does that mean? By far, most real numbers are not algebraic. Examples. the small definition first. A real number that is not algebraic is called, anyone know?
Transcendental.
Transcendental. Right? So if a number is not algebraic, it's called transcendental. These are pretty much the numbers that cannot solve a polynomial with integer coefficients. There are an uncountable number of them. So these guys outnumber those guys, and they outnumber them by far, right? These are uncountable, the algebraics are countable. Which means by far, most of the numbers on the real line cannot solve a polynomial. It's actually quite an exotic property to be able to solve a polynomial. Examples, pi and e are transcendental. They do not solve any polynomial with integer coefficients. The proof of that is slightly complicated. We're not going to go into it, but I just want to mention that. And it turns out that most of the population, if they have any mathematical maturity, will only know about these two guys. When really, those are the kind of guys that most real numbers are made out of, right? So for most people, all the numbers they've ever done in math up to in their entire life, they've only been playing with a very, very, very small subset of the real numbers. Like most of the real numbers that are out there, they don't even know about, right? Some people might know about pi and e, but it turns out there are more numbers like pi and e than there are numbers that can solve polynomials, right? So people might know about 1, the integers, the rationals, radical 2. They know about all these numbers, but they're all countable numbers. Right? They're countable, right? So actually, all your experience with the real numbers up to this point has been with a subset of real numbers that is pretty much like nothing compared to how many numbers they actually are. Right? So yeah, you actually know nothing about real numbers, basically is what I'm trying to say. Right? So most of the real numbers are like 2 of the real numbers that you deal with, but for the rest of your life, you're only dealing with a very small subset of real numbers. Right? So in calculus, you didn't really do anything. Some other examples, not many people know of other examples, but basically constructing numbers from these guys, you can do it pretty easily. But there are some other, you have to actually be really creative to construct them. That's not just a reimagining of these guys. So things like pi to the e to the pi, or something like that, you can mix e and pi together to sort of get something that's transcendental. Here numbers, things like ln2 is transcendental. Things like 2 to the radical 2 is transcendental. It cannot solve a polynomial. Things like I to the I is transcendental. It cannot solve a polynomial. I itself is actually algebraic, right? I solves the equation x squared plus 1 equals 0, right? So I itself is transcendental, but I to the power I itself is algebraic. But if you raise it to the power I, it's actually transcendental. There is something called the Liouville's constant. Liouville's constant. It's basically this number. Sum from 1 to infinity of 10 to the minus k factorial. Which basically looks like 0.110001. Basically, the number looks like 1 in the n factorial place, 0 otherwise. Right? So after the decimal point in the 1 factorial place, in the 2 factorial place, in the 3 factorial place, in the 4 factorial place, in the 5th factorial place. Those places all have 1s, everywhere else you get 0. It turns out that that number cannot solve a polynomial with integer coefficients. And there are a lot of other numbers where we have to be like all these exotic constructions to sort of figure out what these numbers are, when by far most real numbers are these kind of numbers. But to actually figure them out is actually quite difficult in general. And to actually prove when you found one is quite difficult. So, yeah, a lot of real numbers, we have a lot of real numbers, but most of them are inaccessible. The real numbers we play around with all the time are very nice, and they're a very small subset of real numbers. So that's just a little bit of mind-boggling. So we're talking about, oh, these huge infinities, but we really play around with nothing. Like all the maths we've been playing around with, it's nothing. Like the number we play around with, it's nothing, they're nothing, right? Okay, let's move on. The important theorem. You've used this theorem back in pre-calc when you were factoring polynomials, so I won't go too much into using it, but I'm just going to use it to prove some other facts that we already know how to prove. It's called the rational roots theorem. The theorem says, suppose R equals, I think, C over D solves the polynomial. Where Cn is, of course, not 0. All the Ci's are integers. C and D. We can assume we can put R in lowest terms. No common factors. Right? So suppose we have a polynomial. We know there's some, if there doesn't have to be a rational solution, right? So I want to emphasize that first. You don't always have a rational solution. So basically where we're talking about here, we're saying if this solves this polynomial, right? So pretend there does exist a solution. There might not exist, but if one exists, actually know what it has to look like. So if we suppose that this solves that equation, then we must know two things. C must divide C0. And D must divide Cn. i.e., your C over D will have the form plus or minus a factor of C0 divided by a factor of Cn. If a rational solution exists, it has to be that form. I won't do the proof, but it's pretty simple and it's in your book. If you replace x with C over D everywhere, what you can do is multiply both sides by D to the nth power. That will clear all your denominators. And if you solve for the first term, you'd be able to factor out a D from the other side. If you solve for the last term, you'll be able to factor out a C from the other side. And that's going to show you have this division relationship. It's not a hard proof, but I won't go through it because I can't bother writing it down. So that's called the rational roots theorem. If a rational solution exists to a polynomial, it must be of this form, right? And you sort of use that to factor polynomials back in pre-calc, right? Where you look at the factors of the constant term and then you sort of say, oh, x minus that divides into this guy and blah, blah, blah. Right, so you were actually using the rational roots theorem. What else do I want to mention this? It's probably corroborated. if R and Q solves the monic polynomial. Monic just means the leading coefficient is 1. It's just a fancy name for that. So monic just means the coefficient of the highest degree is actually 1. Then R must be plus or minus a factor of C0, which means it's an integer, right? So a rational that solves a monic polynomial would have to be an integer. And again, I'm emphasizing this is if a rational solution exists. Not all polynomials have rational solutions, which we're going to use to our advantage actually. So here's what I want to use. Example, claim. Not anything crazy, we actually know this already. Radical 2 is an irrational number. It turns out proof using the rational, let me call it R T, the rational roots there. What we do is consider the polynomial x squared minus 2 equals 0. Right? If a rational solution exists, then by the rational roots theorem, it must be among the following numbers. It has to be plus or minus 1, or it has to be plus or minus 2. According to the rational roots theorem, those are all irrational solutions. But none of those actually solve the equation, right? You plug in 1, you get it's equal to minus 1, not 0. If you plug in positive 1, it's equal to minus 1, which is not 0. If you plug in 2, you get 2, which is not 0. If you plug in minus 2, you also get 2, which is not 0. All your possible rational solutions are these guys, but none of them work. However, radical 2 is a solution, which means it's not rational. You can see that. It's not rational, right? According to the rational roots theorem, all irrational solutions have to be like this. None of these are a solution. Radical 2 is a solution, but it's not one of these. It means it's not rational, right? And that's actually a full proof, using the rational roots theorem as a lemma, right? So basically, you come up with a polynomial, show all the rationals that can solve it, and then show that this guy solves it. It's not in that list. It can't be rational. Because this is the list of all potential solutions. Right? If you're not in that list, you cannot be a rational solution. That's what the rational roots theorem tells us. So it just provides another way to prove irrationality. That's how we're going to use it. I'm not going to ask you to factor in polynomials. That's beneath us. Okay, so another example, I wrote down a weird number. So earlier I wrote down a weird number. So here's a claim. This number I wrote down, the cube root of 3 plus radical 7 is, it's actually irrational. In proof, I can say the only possible rational solutions to, we looked at this equation, are, now if you sort of expand the brackets, you get 3 squared as a constant term, which is 9 minus 7, which is 2, right? So the constant term would be 2, and this would be monic, this guy would be 1. So the only possible ones are plus or minus 1, plus or minus 2 are the only guys that can solve it. None of these solve it. But this guy does, which means by rational roots theorem, this guy has to be rational, because it is not in the list of possible rationals. So rational roots theorem ends up having us, we can prove that things are irrational pretty easily by just trying to construct a polynomial. I showed you how I got from here to here. So basically, if you want to prove something is rational, try to construct a polynomial from it by taking powers to get rid of radicals and things like that, and try to get a polynomial with integer coefficients. As long as you can do that, and you can show that it's not in this list, you can prove it's irrational. Something I want to mention. There are crazy numbers. There are a couple of problems in the textbook, like this. I don't think I assigned them for homework, though, but I thought I'd just mention it. Beware. There are rational numbers that don't look rational. So we expect when we see a rational number, oh, it'll be a fraction. It will be obviously p over q, blah, blah, blah. It turns out that not all rational numbers look that accessible. So for example, this number here, that's actually a rational number. In fact, it's the number 1. Right? And you can go and start constructing polynomials and you realize that this guy is actually the number 1. Right? It doesn't look rational at all, does it? But it is. Right? There's a problem in the text where it actually asks you to prove that it's rational. There's another one, this guy, 4 radical 2. That's also rational. In fact, it's the number 2. Thought I just mentioned that. So beware of judging things by how they look. Don't judge a number by its cover. Right? Some crazy looking numbers end up being irrational, but then some crazy looking numbers end up being rational as well. So try to be very careful. One recurring theme here is even the quote-unquote obvious has to be proven at some point, because your intuition can lead you astray all the time. That's pretty much what I want to do for the second section. The third section has some interesting things in it. The third section starts to focus on the set R. Section 4 is really where we want to be. Section 4 is going to talk about the completeness axiom and Archimedean principle. through which we can figure out that R actually has no gaps like Q has. Right? So the thing that makes R different from the naturals and the integers and the rationals is that it has no gaps. It fills in all the gaps on the number line. But to see how it does that, we need this fourth section of the chapter. So basically, the idea you want to sort of think of R is like R is the completion of Q. It turns out if you take the number line and you plot all the points that are in Q, it turns out you'll miss a lot of points, right? In fact, you'd actually miss more points than you actually hit. The amount of points you hit will actually be like nothing compared to the amount of points that you miss, right? So there are gaps. When you fill out Q on the number line, it has gaps in it. The gaps are huge, right? If the smallest number system that fills in all the gaps is R, right? Therefore, you can think of R as the completion of Q, right? Take Q, fill in all the gaps on the number line, you get R, right? And the way we know it does that is through the completeness axiom, right? It's basically the axiom that says it's a complete number system for the number line. Right? And section 4 deals with that. So, in section 3, though, we'll talk about the field properties and the ordered field properties. The sets Q and R are, do I mention ordered fields here? Yeah, ordered fields. So first let's talk about what a field is, and then we'll talk about what an ordered field is. A field is a number system and notice I put number in quotations because there are things that are fields that are not real numbers. So let us. So here, without further notice, we can consider A, B, C to be a member of R or Q, depending on how you want to do it. So here are some properties. One, there's closure under addition and multiplication. I.e., if A and B are elements of R, then A plus B is an element of R, and A times B is an element of R. Right? So the first thing you have to do to even consider something for being a field, it has to be closure under two operations that we call addition and multiplication. And in the case of R, the addition and multiplication is the regular addition and multiplication, but we can actually define addition and multiplication to be something else. Probably a good example that a lot of you will appreciate now that you're doing linear algebra are matrices. Like, addition and multiplication for matrices are actually defined, well, multiplication at least is actually defined in a very weird way, right? So the idea of how you define these operations, these pluses and minuses, these plus and times can be very exotically defined, depending on what you want to accomplish. So in matrix multiplication, you realize that you can multiply two matrices, they have to be conformable, which means the number of columns in the guy on the left should be equal to the number of rows in the guy on the right. And in that case, if you multiply them, then you end up with this formula, this complicated formula where you have to take dot products of columns and rows. And that's because in the case of matrices, the multiplication is supposed to capture a certain property. Basically, well, as you now know in linear algebra, you can think of matrices as linear transformations, right? They're just functions from one set of functions, polynomials, to another set of polynomials, right? Where the columns, the number of columns represent the dimension of your output, right? And the number of rows represent the dimension of your input. And that's why you need the number of columns here to equal the number of rows there, because you need the output of the first function to be able to fit into the input of the second function, right? So multiplication in matrices is supposed to be a composition of functions, and that's why it may or may not have some of the properties that we can list here, right? So it depends on how you define these operations. It really depends on your definition. But for the real numbers in Q, when these guys are defined as you know it, the following properties hold. And so I just want to mention that because it's going to be like, well, obviously that way, but it's not obvious, right? There are other number systems where these just don't work, right? But in the case where you can define operations such that these work, we call such a number system a field, right? So the set of all matrices is not a field, by the way, because it won't fulfill all these properties. So here are the properties. The properties for addition, they're prefaced by A plus B plus C is equal to A plus B plus C. This is known as the associative property of addition. For all ABC, this is true. Another thing that addition must be able to do, it must be commutative. So addition should work no matter which order you add it. Add in 3. There exists 0 in R such that A plus 0 equals A for all A. 4. And again, depending on 0 is always not an obvious choice for addition. But again, in linear algebra, I'm pretty sure you'll have examples of these already, where you define addition in such a way where filling out everything with zeros actually doesn't work as 0, right? Because you can add it to something and you don't get itself, right? So if you can find an element such that adding into anything gives itself, you can find an additive identity. That's a property of a field. In the real numbers at Q, 0 happens to be that number. In other systems, it might be something entirely different. For each A, there exists something called minus A, such that A plus minus A gives us the additive identity. Right? So the existence of additive inverses, or negatives, as we call them. There are properties of multiplication, like associativity. Another property of multiplication. Commutativity of multiplication. Right? And here is a guy that doesn't work for the system of matrices, for example. If you take the matrix A times the matrix B, it's not always the same as the matrix B times the matrix A. So this doesn't work for the set of matrices. The set of matrices is not a field. There exists a number that we call 1, such that if I take A times 1, the result is A. It's called the multiplicative identity. The other guy is, for every A not equal to this number that we define here, there exists an A inverse such that A times A inverse gives us the multiplicative identity. There's also a property denoted DL, stands for distributive law. A times B plus C is equal to A times B plus A times C. for all A, B, C. So this is the definition of what it means to be a field. Any system that has these properties is called a field. Right, those are the field properties. So some fields are obviously Q and R, as I mentioned. What about the integers? Do the integers form a field? What breaks down? M4 breaks down. The integers are not a field, right? They fail M4. Right? Naturally, the naturals would not be a field either because they would also fail M4. They're also not closed under negatives, right? So it's possible for it to take one natural number and it will have no negative. In fact, no natural number has a negative. They're the only positive integers. Not a field, set of all matrices.
What if you take Z modulo some prime number?
You tell me.
Seems like it would be good.
Yes, Zn is a field. Is it a field for every number, though, is probably the question.
If you look mod 4, if you pick 2 mod 4, there's no number that you can multiply 2 times equal 1.
That's correct. So Zp, where P is prime, is actually a field. Zn, where n is not prime, is not a field. So we take these for granted because we've seen them all the time and we've been playing with real numbers all their life, but it's actually an exotic thing to actually have these properties, right? There are a bunch of things that don't, right? And the farther up you go in mathematics, the more you'll start to deal with these things, the guys that are unfamiliar in terms of property, right? So don't take these guys for granted. They're actually, it's pretty important to be able to fulfill these guys. There are 9 properties. Did I list them all? Yes. Okay. So that makes a field. An ordered field is where we're going to define less than or equal to and what that means, and we'll do that next time. So, we'll stop there for now.